directed graph elements can be an expression of, or a way of expressing, the relationship between error and the local instantaneous gradient of the weight proportional to the amount of error generated by it. So each coefficient is proportional to its linear regression capacity. This version over here on the far end implies the relationship of the square of that system, and we're going to say that something like mean squared error is a version of this system, but the difference here is that rather than just using something like square error for association and attempting to use the minimization for calculus on the global level, we're only going to be able to update this at the local scale. You can only see that which is immediately around you. So especially whenever you go into higher dimensional space and you start vectorizing these relationships, the big difference is in a one-dimensional space, we can imagine it being very much that simple parabolic dish, right? Moving down the error surface. What does it look like in 3 dimensions? It looks like that conic sort of structure that we had earlier on. What does it look like in 4 dimensions, 5 dimensions, 6 dimensions? We don't know anymore, right? We can't even visualize it. So what we mean by what is up and what is down is just going to basically be a independent component analysis, looking at it relative to how much each weight has to be updated in order to maximize the global system. This parameterization of the amount that relative gradient of error is contributing to the weight update process is called the learning rate, once again. And that learning rate is an adjustable parameter that can be adjusted by a variety of factors. So we can either adjust it over the duration, right? We could say that as the network trains further within the system, we might want to slow it down a little bit. Or we might want to do something that is called simulated annealing, right? Where we intermittently add a little bit of extra energy to that system, right? Allowing it to escape local minima. So whenever we have potentials for multi-optimization systems, the other thing that we run into is that a minimum provided for a derived functional output does not necessarily mean that it is the minimum of the entire continuous function. So since the function can change multiple times over its entire range, right, we could get stuck in some region where it seems like we've reduced the total error to a minimum, but in fact there exists a total minimization of error at another location and we have to escape it. Also, as we're getting toward the bottom of something that is very steep with respect to those error curves, we might want to slow down the process so that we don't overshoot the bottom, right? We don't want to be up here and then go like this all the way back up to the other side and like this, like we're at a skate park, right? Coming down off the sides, right? And then just slowly stop in the middle, right? We want to slow down. We don't want to take huge steps because those are going to create additional error in subsequent steps. It's going to mean more steps. What does more steps mean? It means our particular function, our particular neural network as a composite of functions will not come to a conclusion that provides us with a satisfactory minimization of our desired target as quickly. It won't learn as fast. So we want to try to optimize that relationship of that learning rate such that we arrive at the solution as quickly as possible, but not go so fast as to skate over the solution and miss it. When we think about node architecture with respect to these systems, once again, this is a review for us in the discussion, that this loop here is the update process for some weighted system such that the update of the weights within the system are established based upon the difference between the desired activation at that specific node and the activation that was output at that particular position. Now, the reason why I say that every node has a desirable output, we don't necessarily know what that desirable output is, but we know it exists. Especially whenever the element is hidden further within the network, we don't always have a direct map between what that particular neuron's activation is and its relative contribution to the entirety of the system's error. So we're going to use mechanisms to be able to determine who's at fault here, right? We have an entire room full of people, each one of them doing some level of observation relative to their input, and everybody is contributing, voting, recognizing something, and then passing off that information to the next person. When we get to the very end of that system, the bucket chain of information, right, we're going to have a relationship between what we hoped we would get at the end of the system and what we actually got. So creating a mechanism to totally reduce all relevant error from that system is virtually impossible, but at the same time, we can at least get down to the bare minimum of determining who is the most to blame. Now, the immediate answer is probably everyone is to blame at least a little bit with regard to most neural networks. What I mean by that is that the initial process of seeding the values for the weights is, as described previously, a random process. So we randomly initialize the weights within the system. So the initial state of the network at its very first pass through of the data has what? Random weights, thus the output is effectively random. Though there's an interesting relationship is that we often see something very closely modeling a normal type distribution of the weights within the network. So all we're really going to be doing is trying to get the network to level back out or balance back out to those distribution characteristics. Where do we borrow those from? Well, both from the activation function relationships to one another, right, as well as our understanding of natural, exponential, and logarithmic processes, right? Probability density functions are based upon our understanding of smooth transitions between ranges. We'll talk about that in just a minute. We're going to go through the probability functions and what of them we need to remember, what of them we need to recall. We'll also go through some of the, I guess you say, the precursor mathematics. What I'm going to do is I'm just going to rapid fire through linear algebra for you and say these are the things you effectively need to be able to do at some level with this process, and then we'll pick those out as we go through it. So remember the activations, right, which are the function that apply to the summation of the weight input network, are also these selectable items, right? You don't have one specific activation to work with, and various networks can learn at different rates relative to which activation is supplied. 3 activations are supplied here, all right? What's the main difference between the logistic and the hyperbolic tangent function? Anybody remember this one? It's simple. It's just where it's shifted to, right? Yeah. That tangent allows positive and negative outputs, right? Tangent in general allows neg pos, so it's in both the second and the third quadrant of that element space, right? Whereas the logistic function shifts up by that half-step characteristic such that the minimum operational output of the logistic operation is 0 and the maximum of it is 1. Now, what do we use logistic functions for? Binary classification is one option, right? But what is one of the reasons why it's more desirable than linearity? It doesn't have negative elements at play, right? Or very large positive elements. So if we're going to do it, if we're to think about it just from a strict standpoint, if we have 2 classes, and we're going to describe them as 1s or 0s, the boundary between those 2 spaces could be a very hard boundary, as iconified by the threshold function, which is a step function oriented around 0, right, in which we step from the lowest to the highest value immediately. Now, the step function can be initialized in a lot of different ways, either low activation at -1 operations or greater than 0 operations above 1. Effectively, the situation described here is either either the range is from -1 to +1, or the range is from 0 to +1. The difference largely is based upon whether or not we're attempting to simulate activation, right, and inhibition. This idea of inhibition is that some neurons within the brain, some neurons, biological neurons, are those that excite, right? They say, hey, look at me, look at me, look at me, right? And some of the other network elements are the downer neurons that go, I'm not going to get excited about that. I think you should settle down. Settle down, network, okay? The inhibitory, those are the inhibitory elements that actually are looking at it and saying, whoa, 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 hold on. You're getting out of hand. I actually see the opposite of what you're looking for, right? I see the exception case. So many times an inhibitory neuron is designed to detect exceptions to a rule that another excitatory neuron is designed to detect. It's really weird, because additively what happens to a +1 and a -1? It goes to 0. What's the quality of the activation at that point? Nothing. It levels itself out. So in some cases we can have networks that entirely work upon just positive activations, and then we level the network out by re-weighting the system. We say, okay, we know everybody here is very positive, so we're going to have to scale down, right? We know that if we keep summing together, if we sum together all at high values for positive outputs, the summation is going to explode, right? Interestingly enough, if we think about this through the idea of like reviews for some kind of website of some kind, right? Let's think about just the idea of a YouTube video. YouTube videos get ranked up and down. How? Thumbs up versus thumbs down. Yeah. Excitatory, inhibitory. Okay? So the summation of the activation operation oftentimes influences the degree to which that particular video is recommended to other users. So it is an incorporation, additive process, and if one person gives it a thumbs up, another person gives it a thumb down, its effective sort of engagement level, it should be flat. Interestingly enough, though, YouTube doesn't care whether or not you love it or hate it. Okay? So it says we're as much, hate sells as much as love, okay? And they figured out how to totally monetize that concept within their development schematic, which is, I don't care whether it's an inhibitory or excitatory response, I'm just going to take its absolute value. So structurally, we might actually treat the net function operation of a thresholding as something like a hard option in one direction or another. Whereas something like a logistic operation is going to be a probability-based assessment, where we have a continuous space of possibility that has a center definition that tends to push elements that are above or below its center off to one direction, either up or down with respect to the likelihood of being a member in a class. So if you think about a boundary in general, any boundary, you can think about it as saying, what is the likelihood of it still being your yard if there is a fence there? So as you approach the fence, what's the likelihood of it still being your yard? Right? Effectively, it goes down as you approach the fence. Then you jump over the fence on the other side, what's the likelihood of it still being your yard? Right? It drops off. Okay? It drops off. So wherever that fence is, maybe that fence wasn't placed exactly on your property line. We know that happens. So what we're describing is that sometimes we can place it in the right location, or sometimes it might even be a little bit more nebulous or vague where the line starts and stops. But if you don't have a fence, right, then you say, is it your neighbor's yard or isn't your neighbor's yard? As you're mowing through the yard, right, and you go, am I now mowing my yard anymore, or am I mowing my neighbor's yard? Okay? It's like, it's good as you're far into your yard. Very obvious you're far into your yard. But as you get closer to what the property line is, it gets more and more vague. And then will increase in probability of being your neighbor's yard as you get closer and closer to their house. So when we're thinking about these smooth transition operations, it's really about the likelihood, probability for an undefined space, which most decision surfaces are not hard like this one. They're in fact relatively fuzzy. So we went from attempt to try to mimic biological neurons, strict adherence to probability operations, and then very hard operations based upon either inclusion or exclusion, binary input classification. So those are three options. Are there more? Absolutely. Nuts amounts. Okay, there's probably like 20 or 30 that I've seen out there. I've seen lists of comprehensive lists. Rectified linear units, specialized linear units, ALUS, ATOM, and other mechanisms for creating activations for specialist cases, both an activation and a backprop solver involved with the system. All right, now we're scared. Now we're scared. This is the scary slide. Backpropagation in and of itself is a mechanism of determining exactly how much at what point relative to the entirety of the error of the system that a specific element within the network is functionally contributing. This is a graph-based, I guess you'd say, approximation of a single neuron taking in an array of inputs, and then we're going to describe the relationship between the net activation element K, the weight at operation relative to the gradient at a specific weight within the system, right? That would be the weight of activation between the neurons as described here. And we're going to say that that net activation K is respective of a partial activation of the net for Y output, right, relative to the partial of the Y output with respect to the entirety of the error experienced at the end of the sequence. This is part of what is called the chain rule, all right? I'm not getting into this in depth. We're missing pieces, right? We're missing pieces. I recognize, I know that whenever you look at this and you go, that's a lot of symbols, all right? Anybody watch the videos, the 3 blue, 1 brown videos I put on? Okay, you might have seen it in another section. He does an incredible job of breaking this down, all right? That's probably the best job that could be done. I don't think I can ape it in this class because I'm not able to do the kind of closed form manipulation. I mean, I could try and videotape all of our lectures and highly curate them and edit them like he does for his videos. But what I'll say is this: the process of teaching in a classroom attempts to be very organic, right? I'm looking at your faces, I'm seeing what is hitting, what's of interest, what's not, and sort of moving through this space. His implementation and approach is more open form, but he has a lot of visuals that I don't really have the ability to manipulate within here because there's too many moving parts to keep track of. But the key is this formulation is actually very similar to the formulation that he puts forward in the second operation version of his proof video for backpropagation. We will go through all that math. I effectively have to do it on the board, but there's, as I said, pieces missing from our discussion. This is the goal, this is what we want to build up to, and what we ultimately are going to do is we're going to use a matrix form of the solver to create a closed form version of the solver that we can calculate within our algorithmic setup. One of the goals within the next couple weeks is for you guys to have enough of this foundation, both with the mathematics and the algorithmics of the approach, that you'll actually be able to start working on coding your own version of a neural network. All right, we're going to start off by coding a neural network from scratch. Then we're going to install and start manipulating with the libraries, the common libraries that are out there. And then we're going to compare our attempts at creating those networks to the ones that are out there in nature, right, in the natural space, right? I say one of the things that's interesting about the approaches that are out there on, within something like TensorFlow or PyTorch, they're amazingly optimized, right? Every attempt to try to clean up each of the operational characteristics of that system has been refined down to an absolute mirror shine. We're probably not going to be able to get to that level of sophistication because we don't know all the necessary tips and tricks on exactly how to perform and implement each of those matrix operations in the perfect way for that sort of library or space. But we can leverage based upon two things. One, we can understand it better whenever we attempt to make it ourselves. Two, we can attempt to try to incorporate our understanding of what we didn't do with what was happening and seeing sort of how that might be benefited. We're going to, and I'm going to give you an assignment for this week, to utilize the TensorFlow Playground website that we looked at. Those of you who have already done it, I'd like you to take on in a different way, right? Maybe to take the parameters that you found in your previous endeavors for it, and then now with sort of a new appreciation for it, build your own experiments to refine your understanding, right? Ask better questions about how many elements per layer. Ask better questions about what the activations mean and what they're doing. The investigation is going to be sort of an immersion process where you're going to try and build that network, right? And then you're going to be asking yourself, why does this one work and this one doesn't? In many cases, everything breaks down to that, what does it not do that I want it to do sort of question. skip the slide. Multi-layer neural networks are interesting because a simple 2-layer network doesn't necessarily have to follow the strict operational paradigms of the backpropagation. You really can sort of forward solve a simple network. With only a couple layer elements in it, you can just use exhaustive methodologies to determine optimal parameters. But once you get up to the extreme multivariate spaces, where you're attempting to describe connectivity of fully connected networks in continuous systematic regions, there's really a problem in which it says that there is an issue with sigmoidal activations, and having enough number of nodes that are universal mappers are capable of approximating any continuous decision region, right? So that's what we said previously, is that if you have enough elements that you can describe the interaction or relationship of any arbitrary functional linkage between two aspects. You guys all understand the concept of a mapping function, right? It takes a range of inputs and then maps them to another range of outputs. Some systems for mapping functions are linear, some systems of mapping functions are nonlinear, and the relationship between the weight matrix and the activation function is going to composite together, either to create linear or nonlinear operations, and we can just keep compositing them together. The problem becomes that there is not a clear understanding, a direct clear understanding between the linkage of the exact weights within the system and a perfect subset of them, right? You can't closed form solve something that has high dimensionality with interactions and relationships. One of the examples that I use here is that differential equations often govern many real-world systems. Populations of animals within the world, right? You have owls, you have foxes, and you have rabbits. The populations of owls, foxes, and rabbits change to one another, proportional not just to the change of one individual group, but proportional to the change of the other groups. So within that system, we can't make a strict linkage, because if we attempt to hold one element static while moving the others, we end up with a problem. So backpropagation actually attempts to overcome this step, or it succeeds in overcoming this step, by determining the relative amount of change as it relates to both elements at the end or toward the end of the system that link directly to the output, as well as the activations of previous layers that function as the input to those subsequent layers. So the process follows the chain rule, right, which allows us to optimize that system. So if we treat any forward pass activation operation process, we can say net or alpha activation for n is the summation for I elements of weights of ni relative to the system n, and is a proportional to the desired output at that particular level. What's one of the situations that we're seeing here at the bottom? We're seeing that the activation level for n, right, the delta of n here, is equal to or proportional to the error of the elements, right, for j of n at f prime of net. So what is at f prime? That's the derivative of the activation of net at that previous layer. So describing this relationship of the error as it relates to the input versus output layer, right, describes what's happening, what's coming into the node versus what's going out of the node. And we're going to say that the activation, or the delta of that network element, is the summation of that weight at that input layer element, right, relative to the activation at the subsequent secondary element. So for the forward pass process, error is related to what? It's related to the scale of that particular weight matrix, or weight element in proportion. So as each piece of information gets passed off from one layer to its subsequent layer, the error process is summational, such that anytime there is a difference between the weight that is the ideal weight and the actual weight that we're calculating with, we have what? We're integrating error. So this is a portion that says that the integrated error within the system in the forward propagation layer adds to or is summational to the ultimate error within the network. So if that means that everybody's small amount of error, right, the difference between that weight's ultimate output and its contribution to the total summation of the activation, right, the cost function, that is the difference between what we want and what we got, can be sorted out by taking the derivative or the degree to which that particular change in value at that particular weight adjusts the actual total error within the system. So the forward propagation process results in the error, and the back propagation attempts to understand or attempts to regress back via the weight update formula through an inference about the local area of the weight. At some given point, I'm in total darkness, right? I can feel around me. That's all I can really do. This is the way in which uncertain spaces in error operations work. I can't necessarily know what it lies far in front of me because I don't know exactly how a change in the weight affects the total error system. Also, here's the problem. As I adjust another weight, the relative amount of my weight changes the error surface for that particular feature. Now we go, oh no. Oh no. It's a multivariate optimization problem in which changing one, it changes the other. So what can you do? You can only make a reasonable assumption based upon where you are. This actually implies that to a certain extent, every neural network is a greedy system, meaning that it is optimized only based upon its understanding of its immediate circumstances and its immediate next set of circumstances. So it's going to look at where it's at. It's going to summate together all of the errors created by all of the assumptions that it's built within its array of weights. It's going to add all that together. It's going to translate it through a various sequence of activations, and at the very end of the system, it has one total amount of error that is the contribution that everybody played in making the wrong decision. So we're going to work back from that process, including the amount of error calculated, right, the relative activation characteristic with respect to the desired output for the system, such that a weight update, there should be, such that the weight update formula for this system reflects, once again, that original assumption we had in play, that the weights at the previous layer of the system need to be updated based upon the difference between the desired activation and the activation was received. So if I make an I generate an understanding, right, and I pass my understanding off to someone else, and then they make an approximation for it, they pass it off to someone else, right, and then at the very end, they write it down, commit it to memory, and then we compare what we were looking for. Who's at fault? Is it how I explained it, how he explained it, or is it how he integrated the information at play? The reality is there's a little bit of fault in every element of the system, and thus if we can figure out how a small change in the value, right, calculated based upon the localized instantaneous derivative around the point of the current weight value, we can do what? Determine the optimal direction of change for that specific value. And what do we do then? We change it and then we try it again. Then we run through it all, determine how much error we had, change it, and then try again. This is an exhaustive guess and check process. It's a guess and check process. Sometimes the value that you changed a weight to at the previous assumption, right, might look like it was going to lead you to an optimal position. But in fact, as everything else around it changes, your understanding of its local space and local position also change. So pretty much every weight in a system is going to have some contribution to the overall error. It's going to have some amount that it needs to change virtually every single time we're updating the system. And the amount by which it changes is going to be flexible based upon our previous understanding versus our current understanding. Now, one of the things that's interesting is that every time I take a step on the error surface, I do actually understand where I came from, right? I do understand the previous position. I might even actually be able to say that I sort of have an illuminated path, right? I'm leaving little torches on the wall down in this dark dungeon that I'm traversing that gives me a bit of a path back towards where I was previously. But as I said before, it isn't always going to stay exactly static, because the surface is transforming relative to how the other elements are also changing shape. This is a non-Euclidean, non-fixed operational space. This is a manifold when it comes to the operative calculations for this calculus space. Whenever we're attempting to try to minimize the character, yes?
So my question is, you're saying we are going forward, we are calculating forward. It changes the weight, right?
Mm-hmm.
So we are also calculating the backward.
The back propagation is when the weight is updated, okay? We don't change the weight going forward. The forward propagation step, or the forward pass, is just taking the data you have, putting it through your weights, and then determining the output at the end of the system.
Okay.
So the forward pass will do nothing more than just go through and run multiplications, integrations, and activation operations. Okay. Right? There's no change to the weights.
Okay.
Well, the interesting thing is that when we're done training the network, oftentimes we eliminate the feedback loop, right? We want to eliminate that feedback loop, clip it out, because the network is now fixed, meaning that in the forward propagation will be how it runs whatever it's deployed as a model. It becomes effectively a complicated f of x function that has multiple inputs, right? And either multiple outputs or a single output relative to the circumstance we're describing. We call those MI, right? SO, mesos, multi-in, single outs, right? Or multi-in, multi-out, right? MIMOs. So it depends on the way in which that function operates as far as what we're attempting to get it to do in the long run. Its deployment is to provide us with the information we want. We want it to ultimately be able to satisfactorily predict the target elements of interest. Yes, Sean?
Yeah. The thing I was going to ask, as you told at the last, when it goes forward, mm-hmm. It changes the value. It's not static, you said.
Okay, no, I think you're confusing a couple of things for me. When the weights are updated, right? Yeah. Not just one weight is updated per pass, right? When I back propagate through, taking the end error of the system, and I propagate it into the weights of the system,
okay.
I'm not necessarily, I'm going to go ahead and show you guys another slide here. I have other slides that I use occasionally for these. I'm going to use this set. So some of these are good, some of these are not. Some of the order is a little different than what I would optimally present it in. So let's look at this slide real quick. The forward pass operation takes the inputs and generates the net output over here, right? It is, the activation is at the end of this process. What are the activations? Once again, look, whatever the weight was with the summation is put through this. I like the way the guy on 3 Blue 1 Brown says it. He calls it the squishification function, right? All right, so it squeezes it down so it has to fit between 0 and 1.
Okay.
So that means that whatever is going in to the next layer or the next element of the network is an activation that fits between 0 and 1. So effectively, the next element of the network, the input of it, will be a value somewhere between 0 and 1, which is the input of the next layer is the output of the previous layer. Now what happens here at the end of this system? Let's look and see. It is activated, right? So this is what is often called net or Z, okay? Net is the value that we utilize to say summation of the relative weighted output, the inputs times the weights, right? Then I'm going to put this in, I'm going to say net is going to go into alpha, right? Alpha of net, or activation of net. Activation of net is actually given here, right? The relationship as it is going through that nonlinearity, right? That logistic operation.
Yeah.
Now, Interestingly enough, we're going to have a comparison to some ideal state. So supervised learning specifically is what we're describing. We're saying that this set of inputs should build this output, right? But what did we actually get? We got the activation of alpha net, right? Of the actual network. So it says we got the activation, that was what the network guessed, and then we got what we're actually looking for, and that error is there. That is what ends up being the gradient is calculated based upon, okay? The gradient is based upon, and that becomes a surface of each of the element outputs as projected here. So the surface is the construct of increasing or decreasing the weights, this weight vector, the elements of the weight vector. So which of these weights need to be modified such that the summation and the relative activation get as close as possible between the activation that is desired, right, and the activation that was received. So if I want to keep closing that distance, I need to know which of the weights and the weight vector need to be changed and by how much in order to be able to optimize it. This one, you could calculate it by hand. Given a certain number of finite examples, you could take a series of input vectors and calculate the optimal value. This is what we do oftentimes in our linear regression within something like statistical learning, intro to statistical learning course. What we're doing is we just say, oh, well, it's each individual sample's distance from the mean, right? Relative to the output's distance from the mean, we subtract the mean, we recenter everything, and then we establish the slope of that operation. That is a single input relative to a single summation for the system. One activation, one bias, and then the output. What happens whenever you have multiples? Now we have multiple weights to adjust. These are each individual slopes. Remember how complicated it gets to try to take multiple slopes and figure out exactly what each one needs to be such that that surface is optimized. What I'm saying here is that many systems actually imply that if I change W1, right, the relative degree of error of W2 at some specific value might actually change. The amount of contribution to the error that W at point 2 has relative to W1 at point 1, right, versus point 2 could go in half or could double. They are internally interrelated to one another, but in a way we can't quite tease out just yet. The only thing you can do with this, right, this is a single layer model, you can only create structural linearities, right, simple linearities, but you can't create more complex nonlinearities, so like something like the exclusive OR operation, right? The XOR operation can't be completed by this because it can't enclose two completely different spaces. You're going to need more than one sequential element. You have to have a multi-layered system in order to make that operate. Okay. All right, did we discuss bias variance dilemma in here?
You mentioned it.
Okay. I'm just going to go ahead and throw it out again because I think that it's important that there is an implication that the degree to which a model increases in complexity should seem like it should be able to answer the question better, right? More complex the model is, the smarter it is, right? The more it has the ability to provide specific understanding of specific examples. If we think about our memory, if you have a relatively vague understanding of something, you can provide a very general understanding. But if you have very specific examples, you can provide very specific feedback on that information. Now, one of the problems with this is that within modeling spaces, the more complex the model becomes, the more likely it is to provide us with over-complex solutions or over-fit solutions, meaning that they are too exact. One of the serious problems that's going to happen with neural networks is that we're going to get up into degrees of complexity that are going to blow your mind with regard to the number of free parameters we have. For any of you who've done the statistical learning stuff and thought it was difficult to work with 15, 16, 20-degree polynomials, all right, neural networks can have something like 18,000 to 20,000 free parameters just for a simple process like classifying handwritten digits. And those systems don't do it very well, right? It's actually going to take potentially hundreds of thousands to potentially millions of parameters for those systems in order for them to be able to do it highly generalizably. So the next steps of the process that are going to go past this system is going to be, many of the things we're actually going to introduce are going to be to try to offset this problem. Whenever I say bias, I'm implying that the model is really, really good at providing exact answers to that data set. The more a model is exposed to the data set, the more biased it becomes by that data set. Functionally, one of the problems people have with the word bias is what? They associate it, connote it with something like racial tensions or something like that, sexual differentiations, right? So, men versus women, they have bias against the other grouping. We're not talking about that. Oddly enough, it is incorporated a little bit, but the notion is that as you become more sensitive to one specific viewpoint, right, you will take that viewpoint into perspective over another viewpoint. You will not be able to generalize. So variance is the capacity to generalize. I'm oversimplifying these terms a little bit, but within the scope of what we're doing here, everybody should understand that as bias increases, meaning as the accuracy of the model goes up closer and closer to a perfect operability for some data set with regard to either regression or classification output, functionally or effectively, it's typically noted that it will get worse and worse at working with homogeneous data sets, right? Homo meaning same, geneous meaning source. So data sets sourced from the same set, which could be something like training and testing samples, right? Training and testing usually bifurcated from a total data set. Total data set, we inherit it, we artificially break it up by random selection. We get two data sets. What do we say about those two data sets? They should have roughly the same means and the same standard deviations because in fact they are subsamples of the same original system. That system should have roughly the same mean and standard deviation as all possible data that can be selected from the natural world. So we would say then that any one of those data sets would inherit the same properties that should be seen when that model is exposed to data in the natural world. So if the data only works on the training set and does not work on the testing set, we say that that model has low variance, or excuse me, so high variance, right? High variance. It has low bias. Why does it have low bias? Why wouldn't it seem like it would be more biased, right? That's how we use the term. That's how we use the term. Like that's the difference between the way in which we talk about it. We say as bias goes down. So we say, okay, what? What would bias mean? Bias would actually mean the error relative to the training set. Okay? So if nothing more to take away from it is that bias would be the amount of error relative to the specific set, and variance would be the amount of error relative to some new set that had not been seen. So the bias variance dilemma is that the better I get at relating to and completely getting accurate for the things that I can see, potentially the worse I will get at being able to classify things I have not yet seen. It means, largely, that as models stop learning, or at least when models have learned up to their maximum, they begin memorizing. It means a little bit different within the machine learning space because when you have so many free parameters, it's really easy for these systems to sort of actually store the data within their matrices. Large neural networks have so many free parameters that they can store a resonant pattern of one specific example almost just right there, right? In such a way as to have effectively be able to reconstruct all of their inputs. So if we took the network and we turned it around and ran it the opposite direction, many of these networks are actually able to output reasonable facsimiles of the original inputs. You've seen it. That's every generative network that's out there, right? Every generative network that's out there is an unfolded, unrolled network that is using, instead of putting in something, right, we're putting in, right, instead of putting in a picture of a digit, we're putting in which digit we want, and it gives us a picture. The reason behind that is, or I guess you'd say the reason behind a system that would be good at doing that, having stopped slightly before it memorized specific digits, is that if it memorized a specific version of a specific digit, in each case, you would only have one output. But a generalizable version of that network would do what? It would create a slightly different version of the item of interest in each case. So we need both more parameters to be able to stop the system from being able to overfit to each individual case, but we need a few enough parameters, or at least a mechanism of stopping the system from overfitting to the point to where in which we minimize our bias, right? We are going to stop somewhere within the system. We're going to stop somewhere before the system starts to diverge. Many times within neural network space, we're actually going to utilize processes where we keep track of the network at multiple snapshots, right? We're going to be keeping track of the last few versions of the network, such that if we notice a trend where error is going down, and then all of a sudden error starts to go back up, we can backtrack back to the ideal position when error was minimized. Or we can utilize some understanding of the relative rate of change in error, and we can stop the network from continuing to train once it starts memorizing. So that is what we call early stopping, and we usually utilize the error average from an additional holdout set we call validation. So validation-based early stopping is a mechanism by which we use some additional holdout data to stop the network from training before it overfits. Why would I say stopping the network from training early would be any different with respect to the free parameters? We said that it's just the frequency of the input, right? How often the network sees the data that's changing it. Because it doesn't necessarily see all the data at once. It only sees one individual sample at a time. So since it's only seeing one sample at a time, and then it's looking through the entirety of all the data, right, to try to update the weights for all potential options, the more times you go through all the options, the more likely it's going to be able to memorize or to see specific patterns or specific sets and keep track of those linkages to the inputs. So we stop it early before it has a chance to memorize. It's kind of interesting because we do this the same way. Read a sentence over and over again. What happens? Eventually you stop remembering what it actually says and just remember a string of words, right? So the memorization process is just remembering the sequence of elements, not extracting the useful information that that sentence was originally intended to convey. So you have to stop yourself before you read it so many times that effectively the meaning of it disappears in that process of just keeping that sequence in memory. All right, temporally recurrent networks, we're going to talk about these later on. These operate for something like delay line systems. One example of this is the finite impulse response and infinite impulse response constructor systems, right? So delay line recurrent systems utilize sort of hard memories to keep feeding back in those systems. Recurrent neural networks have an arbitrary representation of that dynamic sequential system, meaning that they can remember either one time step previously or potentially multiple time steps previously, effectively dependent upon how much information they think they need in order to be able to make a reasonable assumption in the next step of the process. The argument here is the difference between episodic versus sequential systems. Not all modeled systems are completely sequential. Not all of them are completely episodic. You can think about this like a television show. If you have a television show that you must have watched the previous episode, right, before this, in order to be able to understand what happens, right? You can't just pick up watching Breaking Bad at episode 4 of season 3, right? It's like, this doesn't make any sense. And you're like, it's not supposed to, right? You needed everything up to this point in time to make sense of it. So the argument comes that that is very much a sequential system. So in comparison to unique discrete time steps that might be able to be represented by a simple column vector, sequential models actually require you to have maybe even multiple column vectors indicating the positional characteristics, right, as well as how those positional characteristics change over time. So recurrent neural networks utilize a feedback process by which the output of the network, right, or the processing state of a current time step is fed back into the network so that the system can keep track of what is important from the previous time step, as well as to then process the next sequential time step. So recurrent networks add an additional dimensionality. They take the flat network, right, and they turn it on its side such that now time is coming on this axis. So we're watching the film coming by here, and the network is observing it, right, as the film slides by. Have you guys ever seen a Turing machine? You guys know what Turing machines are? Tape-driven linear systems. We might talk about them briefly. They're a encoded operational system that's said to be able to keep track of any set of sequential forward memory, right? One of the things is that we have not studied these as extensively as other types of static or frame-driven networks. An example of this is that even within the domain of convolutional neural networks, all right, those advancements we're going to talk about later on, there aren't as many examples of temporally linked neural networks as there are for static frame networks, right? So just take for pictures, we have a lot more pictures than we do videos. It's a lot easier to annotate a picture than it is to annotate a video. So one of the problems that we're running into is that if we're going to use supervised learning approaches, it's very difficult to be able to make sure that every time step is accurately annotated and that all relative features have been extracted from it. So we haven't created mechanisms for feature extraction and continuity and analysis as much for time delay and recurrent neural networks as we have for static feed-forward driven neural networks. Traditional TDNNs, as I mentioned beforehand, are a mechanism of forward propagation networks. Edelman-Jordan recurrence is another common mechanism for the recurrent RCSN. But most of these others are just here for informational purposes. We won't study them in extreme detail. But these are some of the relatively historical adaptations and individuals who have worked with them. One of the reasons why this is on this slide is if you've ever had a conversation with Dr. Dereshani, who's the instructor that I took this over for this semester, he did his dissertation on neural networks back in the 90s, all right? So he was actually working in a contemporary of some of the people that were doing this kind of work, right? And some of it even has sort of come along since he's had his PhD in neural networks. So some of the historical emphasis makes a little bit more difference to him. But if you want to know where this comes from, you can go all the way back to Reinblatt and Fukushima back in 1954 as working with some of the first artificial neural networks. And then these guys started picking it up back in the 70s and 80s. Most of these architectures were actually derived long before the hardware was capable of actually running, right? So we're working off of a very interesting space. Kernel memory systems, these are going to be these delay operation systems, actually mimic another process that's very common now, and that is going to be side memory systems such as long-term, short-term memories, and transformers systems, which keep track of certain recurrent subspaces. Notice the mathematics for these and their structural diagrams start to get incredibly visually comprehensive very quickly, and some of the ones that we're going to look at later on are also orders of magnitude more intimidating. All right, these are not even remotely close to the maximum ones. As indicated by this, right? Context layers in something like a Jordan network or an Elman network, in which we have either sequential forward connectivity or potential FIR filters, right, finite impulse response driven generic filters in fully connected structural networks, lattice style networks with an Elman network. Now, why is this morphology with the Jordan network for context layer and input embedding mentioned up here? Because input embedding is the core of some of the natural language processing, NLP, which makes up a lot of what we're going to do with some of the stuff for context-sensitive transformers later on. I did a little bit of work in this area, all right? So my dissertation actually includes memory operations with regard to long-term, short-term memories. LSTMs are a specific subset of dynamic memory storage systems in which there are a variety of different states involved in this process. This is intimidating. I'm not going to lie about this one. This is one of those that I cannot simply describe to you, and there is no flattening. Partially, this has to do with some of the previous output activation layer is kept as a reference for the next activation. Interestingly enough, though, new information can come in and bump off that old information, right? So at the first time step, some element of a sequential array may seem very important. But at the next time step, we may see something else that we go, no, my initial assertion that that thing was important is actually untrue. And in fact, this thing is important. So instead of the original item being in place, the system will actually forget its previous assertion about what information was important. Then it will utilize that understanding of what is now important and will attempt to try to find something of similar relationship to that. One example here is if I see a ball in a video, right? And at the first moment I see the ball and it's static and I go, oh yeah, okay, it moved one a little bit by the frame. We say, oh hey, ball moved, right? But at the third frame of the video, I see another ball come into frame, right? And it's just barely in a frame, right? And then the next frame it's here, right? And the next frame is here, next frame is here, right? You say, oh wow, like the ball that I thought was important, that was doing something of significance and merit, right? It's not, no, I don't care about that anymore, right? I'm going to pay attention to the thing that is most important. This idea of attention is relatively interesting because LSTMs gave birth to another subset of systems that we're going to talk about in some relative depth, and that's transformer-based networks. Right? Transformer-based networks are a lot more complex. Depth within CNNs and DNNs is all about the degree to which there is an obfuscation between the input and the output system. The internal nodes of the process become less and less relatable to what we would consider as significant or having extracted features and patterns that we think are of use. Most of the time, we tend to think about that the deeper the network goes, the more powerful it should become, right? I encourage those of you who have not worked with the TensorFlow Playground to work with it and try to understand what happens as you add more and more layers. You'll notice that your immediate thought is you'll have smoother transitions, you'll get a lot better fidelity of understanding and extraction. With more layers, you should be able to have more learning capacity, right? But in reality, most of the time, more layers make the system just take a heck of a lot longer to train. This has a lot to do with the problem that we'll talk about later on, and that is a problem of backpropagation in which the gradient, that is the relative slope of that specific weight at that specific step of the system, gets smaller and smaller as we get back to the initial input layers, right? So the contribution or the relative contribution of that chain rule of calculus consideration flows forward through this system such that the updates to the values of these initial input layers is so small that the amount that needs to be changed in order to make a useful contribution to reducing the error takes hundreds of thousands of samples and hundreds of thousands of epochs, right, periods of training time, before it will start to actually reduce the total error in the system, meaning that they train very, very slow. This problem is called the vanishing gradient problem. Okay? I don't want to go into CNNs and real deep framework, but this is one of the directions we're heading in. I wanted to make sure that I got through this set of slides because this little stop that we did there at backpropagation, okay, the little stop that we did there is going to imply that we need to know how to do the backpropagation in order to build the network. But I ultimately want you to know what we're going for within this class and why it's called deep learning. And that is that there are several new, relatively recent advancements within the machine learning space, specifically types of neural networks, including this particular methodology, which we call the convolutional neural network. Convolution is a special operation in which we apply one function to another function. Right? It is a probability dynamics-based system, but it is also based upon just a strict numerical operation. Once you understand how that numerical operation works, you go, oh, that's reasonably simple. But whenever you look at the calculus behind it, you'll go, that is awful, and I don't like it. All right? It's true, you will. It's like, no, that does not look fun. All right, but at the same time, I will say that this is the difference between, as described earlier, a neural network with something like 18 to 20,000 free parameters being able to classify one digit from another digit, right? Or something simple like digit recognition or handwriting recognition, with a reasonable degree of accuracy, somewhere in the neighborhood of 80%, to convolutional neural networks solve that problem by creating kernels to identify the sub-features within that system. We're going to talk about it a little bit more about how the idea that kernels recognize sub-features, such that you can see things like circles, arcs, edges, and sub-elements of the model, right, being activated, being found. So at different layers of the system, you're going to see the model finding different elements of the input. As a result of that, we've now created a system by which we've done feature extraction, autonomous feature extraction. If you need to go, you're fine to go, but please don't talk. Please. Super distracting. We have kernels that activate to find certain operations on the surface of the image, and the degree to which we can precisely localize those, both spatially, right, or temporally, if we were to do this with three-dimensional data, will feed forward into a network. At the end of the process, the reason why we need to know how the neural networks work is because even these complicated systems that are capable of, as I said beforehand, the difference is these are capable of something like 99.85% accuracy for handwritten digit recognition. So these are awesome. They're really cool, okay? They do everything, right? This is Google image search. This is the semantic analysis. This is image segmentation. All of the tools that we have to play with for some of our advanced technologies that some of you may have already done implementation on. These tools are easy to access now because the models and methods are very high level. You can implement them and you can implement the workflows. But what I would like to do is I would like to be able to make sure we drill down to understand the conceptual frameworks that build these so that you can make better ones. Because only being able to use the tools that somebody else has built for you is a significant impediment to true research and true development. So if we understand how these work at the lower levels, one of the key considerations is if you look over here on the right-hand side, you see this complicated structure, right, of 3D matrix multiplication. And what is over here on the right-hand side of it? Just a neural network again. Yeah. Almost every system that we've discussed, at the end of the process, is a neural network. Some sort of fully connected layer that identifies, puts out the categorical likelihood, puts out some sort of softmax activation. That is where your classification, that is where your identification, that's where your pattern matching processes are fulfilled and finally integrated, right? We don't want to have to try to measure every single parameter of the input we're looking for. We'd like the system to find those metrics and the metrics that are most optimal for that use case underneath of those specific circumstances. So these CNN models have the option to be able to do that. All right? We've talked about a little bit of these. I'll add these for you. Large language models, deepfakes, right? I'm going to talk a little bit about deepfakes later on in the system. But some of these slides later on are specific examples that you guys can look through for implementations of things like biometrics and other systems. All right? I would like you guys to make sure that you're brushed up on your MATLAB and your Python, and I will assign for you guys that introductory assignment, which is going to be first starting off with the TensorFlow playground. All right? We're going to get used to doing something with it on a practical level. And then the second segment of it is we're going to actually build our own neural network utilizing Python or MATLAB, whichever you prefer. I think probably Python might be preferable for most of you. How many people consider yourself really MATLAB fluent? Okay, that's scary. How many people think you're comfortable with Python? Okay, sweet. Much better, much better. All right, so I actually tasked my TA today with making sure that we have everything that we're going to do in here is going to have a Python equivalency. I know my predecessor, my advisor from during my PhD, Dr. Darkshani, absolutely loves MATLAB, okay? I've used the heck out of it. I know how it works, so if you want to do something in MATLAB, I can totally help you. But I also think that Python might actually be more useful in the field. Most people are looking for Python versatility because many of the free and open source implementations of a lot of these tools are going to be utilizing Python workflows. So brush up on your Python, make sure everything's good with that. Go and do a little bit of basic research on the libraries, and I will throw out some information for you along the way. Look at the rest of these slides if you're interested in examples. I can walk through and talk through some of these examples, but I'm actually going to be pulling them out successively throughout the year as we're talking about specific implementations of some of these modules. So thank you very much, and I'll talk to you guys next week. All right, and appreciate your patience with me. I took a couple extra minutes, but we're getting there. We really are getting there. We've got some fun stuff to look at this semester.